Okay, everybody. Now we want to perform interaction analysis more closely. And first of all, I would like to start with an introductional example again. We want to extend our example in the previous section. So we still have our system behavior Gij. So we can call this our system behavior. This is the system. And this system means this is your real world. This is your plant site that you model, and this is the real behavior with all interactions. Mentioned here are some plus signs. This actually does not have to be in real world. So it could be minus as well. That depends on your real system. Just imagine this system for now on. On the left-hand side, you would see some other transfer blocks. And what are these? These are the control blocks. So this is your real control world. So those are your controllers. So, and what you see as well are the closed loops within here. And we still have input values. They could be WE. Then we have transfer functions, set values, UE, and output variables, YE. So this is our real example. And now we still want to have a matrix on how big this interaction is. And we know that we've decided for relative gain area, and that's why we perform interaction analysis. So we want to get this, get lambda, so the relative gain area. And then we want to evaluate what does it mean for us. And therefore, we are faced to a problem. We know that the output is dependent from the input and the other way around. And that's why we cannot perform it directly beforehand in a theoretical way if we do not know all transfer blocks. So in the previous video, we said, okay, we know the transfer functions, then we can calculate the couple matrix and therefore, and afterwards the relative gain area. But for now, let's assume that we have a real world where we do not know all transfer blocks. And there we have to act in an empirical way, and we have to perform some experiments. And in experiment 1, let's consider this. In experiment 1, we will do the following things. We will do a step change in U1. In U1, with all loops open. With all loops open. That means this loop and this loop, they are cut and they are assumed to be open. And then we wait until the steady state. We will wait until the steady state. And then we define the change in Y. We define the change in Y to K11. Okay, and the change in G1 and the change in G1 is due to the change in due to the change in U1. That's what we want to say. So open the loops, and then we say it's only dependent from the left side to the right side. Okay, that's the first thing we know. We do in the second experiment. We do the following steps. Still, we want to do a step change in U1. In U1, all loops open except for loop 2. So this loop loop 2 is closed. Okay, that's what we want to perform. And after steady state, the following will happen. So after steady state, the following happen. A change in G11 is caused by Y1, or causes Y1 to change. Okay, so let's imagine this loop is open, loop 2 is closed, and then we change Y11. Then it's directly visible that you only change Y1. It's no backward connection to GC, and you have no influence to Y2 because this loop is open. Okay, that's understandable. A change in G21. In G21, what does it mean? Where is it? There it is. A change in G21 affects Y2. So it causes Y2 to change. And by manipulating U2, there it is, you manually restore Y2 to its initial value. So this is what you do manually. And the change in U2 that you performed, so this delta U2, this can be interpreted as does it affects Y1 to G12. This affects Y1 again due to G12. Okay, so you change U2, then you have the backward loop, and then you have the couple from G12, and then you affect Y1 again. Okay. So what we know from this example is the following. This change in G1, in Y1, this delta Y1, where does it come from? Yeah, it's a mixture. It's not only, it does not only come from G11, what is the direct couple. So it's down to G11, but not only, it's down to G12 as well. So plus delta y caused by G12. And there we have our interaction. And now we do the following. We can say that our relative gain area lambda, in this case lambda 1, 1, because we are interested in this interaction, can be interpreted as the ratio between this direct interaction over what? Over the whole interaction, and this is y1, or this, yeah, on the right side of the equation. So over y1 completely. And as you can see, when the whole interaction, it has a value, and the direct interaction has another value, and if it's, if this whole interaction is caused by G11, you would get a value for lambda 11 1. And this means the whole interaction is caused by G11. And that would mean that there's no coupling of those loops. Yeah, and in the next slides, we want to interpret those lambdas again and see what values mean what. Now let's write down some possible values for lambda, the relative gain area, and align this with some matrix that we can say what does it actually mean. So first thing, what does it mean when? So we will always consider lambda 1, 1 for now. So this is our focus right now, and in this example this is what we will use. What is when lambda 1, 1 equals 1? When we remember the calculation of lambda 1, 1, then we can say that y1 is directly caused, or the change in y1 is directly caused by G11. And we have a direct couple. So u1 only affects y1. And this is great news, because then we can control y1 by G11 directly without complication. So u1 is perfectly, it's perfect to control. That's good news. Another thing that can happen is, what is when it's completely zero? Lambda 1, 1 equals 0. That means that the transfer function G11 has no influence on y1. Okay, this does mean u1 has no effect on y1. So this is not actually this is actually no bad news, because this means that u1 is perfect to control y2. So u1 is perfect to control y2 because it has no influence on y1. And in the first example, it's the other way around. So u1 perfect to control y1. So here it's the other way around. In the third example, it's a bit of more difficult, because now we assume that it's actually between those values. So in the third example, we say 0 is smaller than lambda, and lambda is smaller than 1. And then there are two possible ways. So one, is it greater than 0.5 or is it smaller than 0.5? In the first point, we can say that the main effect, and the main effect means G11, is higher than the couple effect. And that's quite good for us. So then we can say this lambda is reasonable for us. So here we can say main effect is higher. The other way around for the second part. So main effect is smaller. And this would be reasonable for us. And this would be not reasonable for us. So within here, we would have high interaction and no direct couple has the main effect. And the last point would be bad news, actually. The fourth part would be what? Yeah, what is when this value is actually higher than 1? So lambda 1, 1 is higher than 1. What does it mean? The direction is the opposite around. So it has no direct interaction. It has an, it's from the opposite. So it's opposite to the main effect. But smaller in absolute value than the main. Than the main effect. And that's why it's difficult to control G1 by using U1. So difficult to control. Okay, that's no good news at all for us. The fifth point would be when lambda 1, 1 is actually smaller than 0. And now we say that the direct interaction, the direction of interaction is the opposite to the main effect, just as in the previous part. So like 4, but the main effect is larger in absolute value than the main effect. So, and that would be not acceptable for us. The direction zone, that would be not acceptable for us. All right, and in the next video, we will consider a real-world example for going more into decoupling systems. For now, we have clarified when is coupling strong, when is it low enough, and when we have to decouple systems and when not.